All right. So welcome back. Welcome back to this channel. In this video, as the title and as the title and the thumbnail says, we are going to learn about um, a paper, essentially a model by Facebook or Meta, I should say, Meta AI Research. So it is called Make a Video. It's actually not completely new architecture. It is pretty the architecture is actually pretty simple for us. We could actually understand. So this video is mainly about watching about just looking at some applications of stable diffusion where stable diffusion is actually used. um so this is a paper called Make a Video, right? So we can I'll put the link of this website in the description. You can actually see some amazing work in this field. The idea is generating video from text. So that is the idea. That is the main idea of this model. So make a video research builds on recent progress made in text to image generation technology, built to enable text to video generation. So using this text to image generation, we are able to upscale this image, or upscale this model to actually generate text to video. So essentially, I'll go through what we'll be doing. Right, I'll just go through what we'll be doing in just a minute. No, it's a very good application of stable diffusion. So the system uses images with description to learn what that world looks like and how it is often described. So we'll create an image to text to image generation model that can learn what the world looks like and how it is described. So based on text, we'll be able to generate images. And it also uses unlabeled videos to learn how the world moves. Right. So we'll have the images and text description. So the model will learn how to generate images and how images can be described by training after training the text image generation model. So while training text image generation model, we'll be needing the image and the description. So let's say we have many images on the internet, and each image will a lot of images will have description with them. It's like a href command. Right. So there will be some description or there will be some description of that image, and we could just take it and train the model. So the model, after after learning to generate images from text, it could understand how the world is described and how the picture actually looks like. It learns to generate images, and it uses unlabeled videos. So it uses unlabeled video data with no description. There is no need of description for the videos, right? It will take the videos and look how and learn how the world moves. Right? It will be able to understand the pattern of movement, how movement takes place, how you can actually go from frames to actually the movement, a smooth transition of these frames. It will learn how to do that through unlabeled video data. Right. With this data, Make Video lets you bring your imagination to life by generating whimsical, one of a kind video with just few words or lines of text. Right, with some few lines of text, we could generate images like videos like this. It is I find this very funny. Right. uh the description is the input is, so this is entirely generated by AI. I mean, if you show this to a like kid, he'll probably think maybe there is a Superman dog, right? A dog wearing a superhero outfit with red cape flying through the sky. So this is the description, very short description by the way. And the trained model is able to generate this very good and funny image. And there is a good demo here. So a teddy bear painting a portrait, you get this amazing video of the teddy bear generating that. And remember, there is no photo there. There is no need of a photo, right? You don't have to input a photo and the model will not generate it. The model will generate the photos, and it will as it is trained on how to generate images, it will use both of these knowledge to generate this pretty good looking, right? Images. And this is like robot dancing in Times Square. I think Times Square is a place in, I don't know, I think it is a place, right? Maybe, yeah, a robot dancing, very realistic, and all these behind the scenes and all that, right? Then cat watching TV with remote in hand. Yeah, so that is pretty realistic too. It is able to learn like different patterns how images look like through text image models, and it is able to understand generate videos based on unlabeled video data. Just have a fluffy baby sloth, an orange knotted hat, and just I heard like this shows that you could add a lot of text images or text data also. I think they have trained a very large sophisticated model because you know they have trained a very large sophisticated model. So you can add as many prompts as you want, as many conditions as you want, and the model will able to generate a pretty nice, good looking images. And yeah, an artist brush painting on canvas close up. So it actually, yeah, these are pretty realistic, right? Also drinking water. All that you can actually see all of these images or videos. I'll show you last one. Stylized, hyper realistic spaceship landing on Mars. I mean, like this looks like like old Star Wars, right? It looks like old animation, right? It is able to do perform human level animation, but pretty old. You know, I mean, like I think it is getting better and better, and hopefully in the future we'll be able to generate very high quality, very good, very realistic videos, right? In the future, in the near future, we are yet to go to that, and all that. You could actually see some nice videos that are entirely generated by AI. It's actually pretty amazing, and you can actually do from starting to magic, like or videos. Give a static image, and get this amazing outputs, and also give this image and predict something like that. It's actually pretty fun, right? Like, and I think it is very hard to believe that even this image or even this video is actually all right. So this video, so taking this video, so the model took this video and it is able to generate these images, right? It's able to generate some very nice and neat images, right? Or videos, right? So we have better representation of text input, higher quality, and all that. So this is the application. It's a very good application of image generation in general, but it actually uses stable diffusion in the backend. I'll come to that in just a minute. So this is the paper. Make a video, text to video generation without text video data. The main thing is we will not have video and text data. We'll only have unlabeled video data. There is no need of description for that video. Just like for other supervised learning tasks, mainly we will have the like the input and the output. So for example, we'll have the text and the image for text image generation, taking a text and generating an image. You will have text and image data, paired text and image data. So you'll have like many images and those description of each image, and the model will learn from that. But here we will not be needing any text to video data. We will be needing text image data, but will not be needing any video text data. So so the model will understand both of these things, how images look and how images move, how videos move. Right. So we propose make a video, an approach for directly translating the tremendous recent progress in text image generation to text to video. Our intuition is simple: learn what the world looks like and how it is described from paired text image data, and learn how the world moves from unsupervised video footage. Right? Make a video has three advantages. It accelerates training of the T2V model. Right. So make a video, it accelerates the training of the text to video model. It does not need to learn visual and multi-model representations from scratch, right? I think yeah, I mean, like I think we'll tell you like something we will not be doing something like multi-model. We'll be not doing like image to video. That will be we have to do like two separate tasks. I think multi-modeling means going from one tasks to like performing like all the tasks at the same time with the same model, right? With one model performing the multiple tasks, we'll be not doing that here because we'll be having separate models for doing separate things. right? That is an advantage of like make a video. It does not require paired text to video data, right? We will not need text to video data, just as I've elaborated. The generated videos inherit the vastness, diversity, and aesthetic, fantastical depictions, etc., of today's image generation models. We design a simple yet effective way to build on T2I text to image models with novel and effective spatial temporal modules. So spatial is actually length and width of the image. So the image is actually it is three-dimensional, but we'll be having like height, width, and depth, right? Like three channels, the length and the width, and the number of pixels. And the temporal is actually in a video, we'll have time sequences. So at each time interval, we'll have a frame. So the more the frames, the more smoother the video. I think we'll have some frames. I think in a video, probably something like 18 frames per second or even higher. I don't know. Let me just search how many. Second, 24 frames per second. That is actually pretty fast, right? 24 frames per second. Right, we'll be having many frames per second per time. As time goes on, we'll be having many time, right? So that is a temporal dimension, right? First, we decompose a full temporal unit and attention tensors and approximate them in space and time. Second, we design a spatial temporal pipeline which generate high resolution frame rate videos with a video decoder, interpolation model, and two super resolution models that can enable various applications to decide T2. In all aspects, spatial and temporal resolution, faithfulness to text, and quality. Make a video sets the new state of the art in text to video generation as determined by both qualitative and quantitative measures. Right? So, that is it. This is the work. I have shown, I think, all of these videos. Oh, so this is the review. Like you can see, we'll be generating these frames, right? The inputs and outputs. Right, our main contributions. We present make a video and effective method. All right. So this is the previous work, text image generation, video generation, and all that. Skipping. So this is the high level architecture overview. Right. We'll be taking a input text. We'll be using clip text encoder. I think I have explained it, clip text encoder. I think I'll just go through it what that means. So in the internet, right, clip text encoder is essentially a text encoder that encodes a text into a specific embedding, just like other text encoders. But we will be having the model, right, making the text as close as possible to that image. I'll just go through what that means. So let's say we'll have like bunch of images, internet, online. So this is I1. So this is T1, right? So let's say we'll have the whole of this image. So what we'll be doing is we'll be training two separate models. We'll be training an image encoder. We'll be having a text encoder. We're having an image encoder and text encoder. So we'll map these outputs to a specific representation or specific vector, right? Specific vector space, let's say. So we'll be essentially mapping these outputs or having a CNN, let's say, right? Or any model to actually get to this, right? Find a feature vector for both of these values. So what we want is we want the dot product of both of these values to be as high as possible, because for this image, right, this text corresponds to this image. Therefore, the dot product of these two vectors, that is the similarity between these two vectors, should be as high as possible. And to find the similarity of two vectors, we'll use dot product. So the higher the dot product, the more similar these vectors are. So we'll be using a loss function like that to actually increase the dot product of these values, and we'll be updating the weights of this text encoder such that the dot product is actually as high as possible. And this could be like pre-trained, or we can actually train simultaneously, right? And we want the dot product to be as high as possible, and that is the clip text encoder. And we'll be essentially doing this, and all that. So this is the encoder. So in the loss will be actually be in the loss. So we'll essentially use a loss in which, for example, let's say we have multiple images. So let's say I1. Let's say we have multiple images. I2, I3. Let's say we have T1. T1, text 1, text 2, or description 1, description 2, and description 3, I3, image 1, image 2, image 3, text 1, text 2, text 3. And we want this to be as high as possible, this to be as high as possible, and this to be as high as possible, because the dot product between I1 and T1 should be as high as possible, because we want both of these to be as similar, because they are similar. And I2 and T2 should be similar, the dot product. The dot product of I3 and T3 should be as high as possible. And the loss function will be the sum of all of this, or the loss function will be all the sum of these values minus sum of all of the other values. So we'll essentially be calculating for this also. We're having some of these values here also. Next, we'll have all of these values. So we'll be adding all of these values, and then we'll essentially calculate the difference to just see how we can able to get the similarity, get similar embeddings, or similar understanding for both I1 or similar understanding for like paired data. So that is the clip text encoder. So we'll essentially be right we'll be essentially having this into a like an embedding. We'll be converting them into an embedding using the model that we have trained above using the clip loss function. That is a clip encoder. And then we'll be using a spatio-temporal decoder. It's just like stable diffusion. We could use stable diffusion. As a matter of fact, I think they have used stable diffusion here. Right? They will be generating frames. So they'll not only be generating like single image. We'll have like a matrix of, or we'll be having let's say 16 images. I think yes, we'll be having 16 frames of 64 by 64 images. So each image is going to be of 64 by 64 dimension, and we'll be generating 16 images that look similar, that look that look like they are in a specific time frame, or in a specific sequence, right? And then the decoder DT generates 1664 by 64 frames, right? It will generate DT generate 1664 by 64 frames, which are then interpolated to a higher frame rate by this function, upper arrow F, and increase in the resolution by I think. So this is the frame interpolation. So essentially what we'll be doing is frame interpolation is, after we have like 3 frames. So let's say we have got a text input, text prompt, and we have generated these 3 frames. What we can do is we could use a fine or pre-trained model or a pre-trained CNN to actually take this image and understand what this image is, and we'll essentially be adding more layers here. So in order to make the image or the transition more smoother, right, we will be using CNNs to understand the motion or what is happening with this previous and the previous and the next frames, and we'll be like adding more frames to make the video more smoother. So we could use a fine pre-trained model or something, and we could actually like add more and more layers. Right, we could actually add more and more frames on this model. We'll be using frame interpolation. Right, we'll be essentially predicting like the displacement or something. We predicting the change, right, using this frame interpolation. We could use a like pre-trained model on. We could train a model on some video data, or even like a RC or something like a 3D CNN model to actually understand the sequential image data to predict the next sequence. So we'll essentially be doing that. And then remember that we have the image size that we currently generate is only of the shape 64 by 64. So they have 64 pixels in the height and 64 in the width. And of course, we'll have 3 channels. And then what we'll be doing is, in order to make this image more clarity, in order to increase the clarity of this image, we'll be using a super resolution model. I have covered super resolution. We could use diffusion. We could use diffusion, or else we could even use like a GAN. Right? We could use super SR GAN, super resolution GAN, through which you can have like adversarial training. we could also do that. So we'll actually be having any super resolution model to increase the resolution from like 64 by 64 to 256 by 256, and then we'll be having another super resolution model, right? We'll be having another super resolution model which will be turning this 256 by 256 images into 768 by 768 dimension, right? We'll essentially be scaling this image into higher dimension and higher clarity. So that is the idea. So therefore, we'll be having a high spatiotemporal resolution generated video y hat. Right. So that is the architecture. That is the high level architecture of these models. And yeah. Right. So that is the thing. So we'll be having like all of these models. So the discriminator, sorry, the decoder, the super resolution, and that. The text image model, prior to the addition of the temporal components, we train the backbone of our model method. A T2I model trained on text image space, sharing the core components with the work of him. I think they're the writers of DALI, creators of DALI. And we use the following network to produce high resolution images from text. A prior network P that during inference generates image embeddings YE given text embeddings XE and BPE encoded text tokens X hat. A decoder network D that generates low resolution 64 by 64 RGB images Y hat 1 conditioned on the image embeddings YE, and two super resolution networks SRL, super resolution L, and super resolution H that increase the generated image Y hat resolution to 256 and 268 pixels represent respectively, resulting in the final generated image Y hat. So it will essentially be, so this is just an explanation of what I have just shared earlier. Right? And here, this is another important thing, spatio-temporal layers. So in order to make our model not just generate images, but in order to generate videos, what we could do is, right, in the previous models where we have actually trained any image models, we have only used like 2D CNNs, right, in which we only have like height and width. Now, right now we have like the 3D dimension. We'll be needing 3D blocks because we have many frames, right? We'll be having many frames, right? As we are going to have like many frames, we are going to train the model on three-dimensional convolutional model. So we'll essentially be stacking all of these values. So we'll be taking each frame and we're going to try to stack them on top of each other. We'll be stacking them. We'll be stacking them all on top of each other, thus creating a 3D data, 3D storage data, and we could actually perform three-dimensional convolutional model on this data. This is actually shown here. Right? The architecture and initialization scheme of pseudo 3D convolutional and attention layers, enabling the seamless transition of a pre-trained text image model to the temporal dimension. Right, so we'll be essentially having like here spatial attention. So spatial attention is actually performing attention on data from like inside this image. So we'll be performing the spatial attention inside these images for these images, for this image, for this image, for this image. Whereas in temporal attention, we'll be performing attention between these different frames, right? We'll be performing attention between frames, between time steps. That is temporal attention also. So we'll be essentially having all of these values, all of these models, spatial attention, temporal attention, and CNNs. We'll be grouping them all together such that the model is actually able to understand how to generate images from the diffusion model, and also how to generate um, how image moves using this temporal attention and all that to enable seamless transition of the video, right? And then temporal attention layers are applied following the spatial attention layers by initializing temporal projection to 0, resulting in an identity function of the temporal attention blocks. Newly added frame interpolation network increase the effective frame rate by interpolating between 16 generated frames and the super resolution. Right? So that is the idea. And yeah, so this is pseudo 3 attention layers. Yeah, so that is actually told here. frame interpolation network. In addition to spatiotemporal modification discussed, we train a new masked frame interpolation and extrapolation network upward arrow F, right, capable of increasing the number of frames of generated video either by frame interpolation or for a smoother generated video, or by pre-post frame and extrapolation for extending the voice length, video length, right? Um, we'll fine-tune its spatio-temporal decoder on the task of masked frame interpolation by zero padding and masked input frames, enabling video upsampling, right? When fine-tuning on masked frame interpolation, we add an additional 4 channels to the input of unit. 3 channels for RGB masked video input and additional binary channel indicating which frames are masked. Right? We'll also be masking just to make sure the model don't cheat. Do not. So that is the idea. And hope you got it. Hope you got this paper. I'll put the link of this paper in the description. So make sure if you want, you can just read it, read the interesting parts, everything. So I think that's it. That's it for this video. That is make a video, a very good application of stable diffusion, right? Our video generation. I think we'll also be covering some more papers on video generation. I think I find it pretty fascinating. Video generation, the ability of other like these amazing ability of models to transition, not only generate images, not only generate frames, but transition, how to actually learn the movement of different things. Movement is actually pretty hard to understand, but the computers could actually do that. There's like so much research going on. I'll probably come up with many more papers in the future. Thank you for watching. See you in the next video.